In this third section for Chapter 13, we're going to look at nuclear fission, mass energy equivalent, and nuclear fission. So first we're going to look at nuclear fission. In 1938, Otto Hahn and Fritz Strassmann tried to create a new element through transmutation by hitting uranium with neutrons. And instead of causing a bigger nucleus, like they were trying to do, it actually split it into two smaller elements. And so they discovered that hitting the nucleus with a neutron stretches the nucleus slightly so that the repulsion of your protons counteracts the attraction of the neutrons, and it splits in half. Somewhat randomly, you'll get a mix of products. They won't always be the same two elements. But as they fall apart, fewer neutrons are needed to keep those two nuclei stable, and so they will actually release some of their neutrons. And those neutrons are released so violently that they strike new uranium nearby, and they stretch those nucleus, which causes them to break apart, which causes them to release neutrons. I think you see how this works. If you get enough neutrons from the first hits coming out, you get a chain reaction, and all the uranium that's there will start splitting apart. You get enough of it there, and you get a bomb. So the energy released from the fission of one uranium atom is 7 million times more than the energy from the explosion of one TNT molecule. So this is a lot of energy that we're talking about. The neutrons released from the fission go on to hit other atoms. If you have enough atoms there, that just keeps going until you run out of uranium. These neutrons escape the surface of the uranium when they get to the edge of whatever you're working with. And if they escape, then they're not going to hit more uranium, and the whole reaction will fizzle out. So you need to have enough uranium there that it keeps hitting enough uranium that you just keep getting more neutrons coming out and releasing. If you don't, it fizzles out, and you might get a small reaction, but not something that would cause what happened with Hiroshima or Nagasaki. So the amount needed to cause a chain reaction is called critical mass. You may have heard that before in a movie. We have critical mass. Well, that just means you have enough there that when the chain reaction starts, it continues until you've gone through all your uranium and released all that energy. When they're built, they often will build uranium bombs in two different parts. They'll have subcritical masses, things that aren't big enough to keep the reaction going, separated, and when the bomb is triggered, they smoosh those two together so that now you have a critical mass. And now if it starts, it will just keep going. So by holding them apart until the last minute, that keeps them from exploding in a bunker while they're waiting. Nuclear fission reactors work with a similar idea, but they keep the reaction from going out of control. So you get a high yield of energy, because remember, this one nucleus is going to give off a lot of energy as you split it apart. We'll talk about why that is a little later. But the nuclear fission reactor has controls in it to keep the neutrons at just the right rate that you get a one-to-one chain reaction instead of the usual like you'd get with a nuclear bomb where one uranium goes off, releases 3 or 4 neutrons, starts 3 or 4 new reactions, which releases 3 or 4 per reaction, which starts 3 or 4 more reactions, and you'll notice that just mushrooms, right? But if you have a nuclear reactor, you're just trying to get a 1-to-1 ratio. And that just keeps the energy steadily coming off without getting out of control. And they do that several ways. And they take the heat that comes off, and they'll take the heat to run generators to produce electricity. And that electricity then provides what people need energy-wise. So the energy going off heats a pressurized water or sometimes liquid sodium loop. It keeps that warm. And then that loop heats another water loop. And that's just a safety thing going on there. They don't want the one that's irradiated to be the one that's generating your electricity, because we're trying to set up a couple of places where things could go wrong and we still wouldn't contaminate anything that we were exposed to. So the next loop, it heats that. That's the one that turns water into steam and turns a steam turbine. And then the hot water that's there will usually be cooled by a river that's coming by. And so that river is never exposed to radioactive material because the loop it's exposed to isn't radioactive, but the loop that loop is exposed to is radioactive. So that middle loop there produces the electricity, and then the river will cool the water that got heated by the radioactive loop.
There are some drawbacks to nuclear fission and some advantages. So there are three main drawbacks. The first is that you're producing radioactive waste, and that waste has to be put somewhere where it's not going to harm people. So what they do with that radioactive waste currently in the US is they take it and they enclose it in glass so that it's now a solid, and they put those chunks of radioactive glass in caves underground. They're far enough underground that radioactivity doesn't reach people, but you can't help but wonder if years from now we won't have people go down there and wonder what these large radioactive glass things are. A second disadvantage is that because the radioactive loop that runs a generator is cooled by a river, it actually slowly heats the river. And you're probably familiar with global warming and all the effects that go on there. We get a similar effect taking place in rivers when we have our radioactive energy producing plants working there. They warm the stream. That causes some species in the stream to thrive that normally wouldn't, and others chance dying. And so you get the biosphere changed in the river that's nearby. And then a third disadvantage is that our nuclear fission requires uranium-238. That's the unstable isotope of uranium. And this is rare compared to the more common uranium-235. So it has to be isolated, and it can take time and expense and the right equipment. And so there's a high cost there. That can also be an advantage, though, because what it means is that it's difficult to get the radioactive material. And so when it comes to making radioactive bombs, we're able to control who has what to a certain degree. And there's always concern that the wrong people will get their hands on the uranium-238 and release a nuclear bomb where we don't want it released. So there are also advantages of nuclear fission. When we're using it for a power plant, nothing is burned. So you're not getting a smokestack releasing things into the atmosphere. So in that way, other than the glass waste we're removing, it's fairly clean. It has a very high energy yield. This is a lot of energy for all the activity that we're putting into the power plant. And it doesn't contribute a significant amount to the radioactivity in the atmosphere, which might seem counterintuitive. Here we're using radioactive power generation, but that doesn't release into the atmosphere unless you have a major disaster. And they've got quite a few checks and balances usually to keep those disasters from reaching the general public. Having said that, in the USSR, they had an explosion that took place at one of their nuclear power plants, and they didn't have those safety measures in place. And so that became a very big mess. That's Chernobyl.
Breeder reactors change your uranium-238 to uranium-239, which decays to Pu-239, and that's fissionable. So once again, you've got something you can use in the reactor to break it in half, break it in two, and you get energy out. And then they can use that for the next 100 years. And so eventually, these may be the future of our fission reactors. Currently, because of technicalities, many countries are not using breeder reactors. The main reason is usually because it's expensive. And because it's so expensive, you're not getting as much payback, and so money talks, and so they don't do them. Albert Einstein figured out why these are working. Why are we getting energy out? And the answer is this. Energy and mass are interchangeable. If we have energy, we can turn it into mass. If we have mass and we lose that, we can turn it into energy. When we take a nucleon and put it in a nucleus, the mass it weighed outside is not the mass it weighs inside. There's some work that happens when we put it into that nucleus and it gets in this stable environment. And that mass is the highest when the proton and neutron is outside the nucleus, and it decreases when you put it in a nucleus. And when that mass decreases, we end up getting some energy out. So we have a mass that decreases the most. And the smallest mass, the most stable nucleus, the one that's built the best, is iron. So you'll notice here on the packing fraction, the iron is the lowest element here. You've got hydrogen, deuterium, tritium, helium, lithium. You've got uranium out to the right. Iron's right there in the middle. That one has the least mass when it's packed in. It has lost the most. And if you look at that in reverse, it means it has the least mass to give off because it's packed so compactly. That mass has already been given off. But you'll notice hydrogen is quite a bit higher here. If we were to put hydrogen together with something and move down towards iron, we're going to lose some mass. As we lose that mass, it turns into energy. Uranium is a bit above. If we take uranium and split it apart into some other elements that are before iron, we're going to lose some mass because we're getting closer to iron. So each time we move to iron, we lose mass. As we lose that mass, it turns into energy. So let me come back here. That energy is equal to the mass times the speed of light squared. The speed of light is a large number, and the energy that is given off is really high. So the hydrogen has more mass per nucleon. It hasn't done enough work to get to the most stable form. And uranium, same thing, isn't as low as iron. So it hasn't done as much work in the packing of that nucleus to give you your most stable nucleus. And so if you take two hydrogens and combine them together, they would fuse together to give you a new element that's closer to iron. They would lose mass and you get energy out. That's what the sun does. If you look at the sun, the temperature is high enough to fuse 657 million tons of hydrogen into 653 million tons of helium each second. That means each second you have 4 million tons of mass turning into radiant energy. That's why our sun shines. That's where the heat and energy are coming from, is a fusion reaction. They're actually fusing those hydrogens together, giving them a nucleus that's a little closer to our stable iron, and releasing tons of energy as the mass is lost. So there are advantages to fusion. Hydrogen is plentiful, it's inexpensive, we can find it everywhere. The side products are not radioactive, they're stable. Helium's perfectly stable, right? You get lots of energy, and it doesn't contaminate the environment at all. So this seems like it would be the perfect way to produce energy for countries that use a lot of energy. But there's some distinct disadvantages. That energy it produces is so much energy, it melts everything we put it in. We can put it in, we've learned to put it in a magnetic field. But the problem is the energy to create the magnetic field is more than the energy that's produced. So while in theory we've figured out how to contain it, it costs us more to contain it than what we're getting out. So they're still trying to figure this out. How do you do a chemical reaction that releases so much heat it melts all the metal you put it in?